mini lessons. This is lesson 57, comparing linear and exponential functions. Here are the for today's lesson. We're going to identify the key words in a linear situation that represents a slope and y-intercept, and use those values to form a linear function, as well as using keywords in an exponential situation to represent the initial value, the rate, and use those values to form an exponential function. And finally, to be able to really differentiate between the two and figure out what that pattern is. And remember, if it's linear, it should have a constant difference, like you should see an addition or subtraction pattern. But if it's a pattern that has multiplication in it, or a division pattern, then that would represent an exponential function. Let's look at our first model, and what I want us to really pay attention to is the way rates are represented in both. So two towns, Centerville has 2,500 residents and Easton has 2,000 residents. Centerville's population decreases by 80 people per year, so that is a rate. And Easton's population decreases by 3% per year. So again, this is also a rate, but what's the difference between them? So with the first one, 80 people per year, that's a constant rate. It's a predictable number. It's always 80 people less per year, whereas 3% per year means I have to know the number before it, and it's going to continue to go down by 3% each year. So it's declining by that rate. So that's a huge difference between these two, and that's our first hint about which of these is going to be linear and which of these is going to be exponential. So in this example, Centerville is linear. Its context represents a linear function, whereas Easton represents an exponential function. So let's look at these and let's write them down as an equation. So for Centerville, the rate of people goes down by 80 every single year. So y equals, it starts off with 2,500 and every year it goes down 80. So I'm going to write that as 80x. So that's our constant rate, and we can recognize it's linear because this is to the first degree. Whereas for Easton, it's going to go down by 3% a year. So y is equal to its initial, which is 2,000, times a rate of a decrease of 3%, so 0.97 to the x power. So that's the big difference. And let's see how this plays in, because 3% doesn't seem like a lot. Like when you compare them, 80 people sounds like way more than 3%. Sounds just like way more. Matter of fact, out of 2,000 people, 10% would be 200. 1% would be 20. So we're talking like in 1 year, 1% would be, 3% would be what, 60 people? So it doesn't sound like it should be a lot of people. So let's look at what happens after 16 years. Because what we're going to notice here is how time plays a factor when it comes to exponential functions. I'm going to hit pause for a second so we can set up our calculators. Okay, I've set up both equations where x is equal to the number of years, and we want to figure out what is the difference between the two towns after 16 years. So I'm going to start with Centerville. 80 times 16 is 1,280. And 2,500 minus 1,280. Go. The town's population is 1,220. So it's a pretty big decline. Let's do the second one for Easton. And again, because this is an exponent, I'm going to write this all as one function so that it doesn't round. I want a more exact answer here. So 2,000 times 0.97 to the 16th power. And I am going to have to round for people, 1,229. So that's our difference. So taking a look, it's a difference of just 9 people. Easton will have 9 more people. I'm going to go back to the original problem now. All right, so how many more residents will Easton have? Easton will have 9 more residents than Centerville after 16 years. And I also just want to note, look at how much of a decline that was. Just taking a look and seeing how much of a decline that represented overall. All right, but let's hit pause and jot this down into our notes. And let's look at our second model problem. In this problem, which we've seen before, we want to be able to recognize which is a linear relationship versus, of course, an exponential relationship. So again, what we are looking for is a constant difference. And this should be represented as either just addition or subtraction. So what I'm looking for in my f of x function is how is it changing? And in this first one, it's changing by 1, then by 2. So already I can recognize that this would not be linear. I'm noticing it's changing, it's increasing, it's steadily growing. Looking at the second one too, automatically, just from the first two, I can see how much is changing by a half, and then by 1, and then by 2. So this is a doubling rule. So this would be a type of 2x function. And let's go to the next one. So plus 2, plus 2, plus 2, plus 2. So this is a constant difference. It's a constant rate where it's increasing by 2. So that is a 2x that we're seeing happening there. And let's look at the last one. Plus 1, plus 1. So it's deceptive in the beginning, so you continue to go. And there you go, plus 7, and then plus 16. So it is grown way more from there, up, not 16 plus 19. So we can identify pretty quickly which would be linear and which would be exponential. Hit pause and jot this down into your notes. And here's our last one I want you to try. You can hit pause afterwards. Consider the pattern here. Look at the growth here. What type of model is being shown here? Is it linear or would it be exponential? And how would you determine the end pattern? Let's say you wanted to know the 5th set of blocks. What would the 5th set in the pattern look like? And explain. So hit pause and jot this down. Okay, and typically what I do to start solving this, if you weren't sure, first of all, this is an exponential function, is I would set this as here's n. Okay, let's talk about the reveal. First of all, this would represent a exponential growth, because if you're looking at the difference between this one to this one, it's increasing by 2, and then this one is increasing by 4. And you could also recognize another pattern happening here. So noticing that my sequence, I have 2 for the first one, then I have 4, then I have 8. So you could recognize that this one is doubling. So if you ever want to just see to the nth pattern, and this is the nth, and this is the number of tiles. So 1, 2, 3, 4. In the first one, I have 2, then I have 4, then I have 8. And if this is continuing doubling, next one is going to be 16. So how can I represent this rule? It is exponential. I can represent this as 2 to the x power. And let's see if it actually works. For the first one, 2 to the first power would equal 2. 2 to the second power would be 4. 2 to the third power is 2 times 2 times 2 again, would be 8. So that's our doubling rule. And 2, although it's not represented here, 2 to the fourth power would then be times 2 again, would make 16. So this is how I can figure out any pattern. I would just make 2 to the nth, where no matter what number I want, I can just make it to the nth power. And that could be my rule. And that's how I would explain it. This represents a doubling pattern. It's an exponential pattern. And I can use the function f of x is equal to 2 to the x power to create any number of squares to the nth degree. Right? That's it for today's lesson, Math Marvel. I hope you found this really helpful and that you're able to quickly now spot the difference between linear and exponential. Those rates should seem drastically different now when you see it in context, either on a graph or in a word problem. That's it for today. I'll see you in the next lesson. Be well.